Good afternoon. I'm excited to tell you our project that allows light communication in the dark. It is joint work with Professor Kevin Wright, a faculty from the Department of Physics, and my advisor, Xia Zhou. Billions of smart devices are around us. They're all going to need wireless connectivity. It's going to be a big challenge for radio spectrum. The potential solution is to look into visible light band. With visible light communication, or VLC, the ceiling lights work like wireless APs communicating with smart devices in the room. Visible light offers greater bandwidth, is more secure, and nicely reuses the ubiquitous lights around us. All sounds good. But what happens if the lights go out? Well, the communication is gone. Definitely not a good news for monitoring applications that require always-on connectivity. Also, think about using VLC on mobile devices. It's awkward to see a light shining on your phone or during data transmission. Not to mention that having the LED on will drain your battery quickly. Today, I want to tell you a technology that we've developed to address these problems. We decided to join the dark side because the force is stronger there. Our solution allows VLC to work even the lights look dark. It's the dark side of VLC. We call it DarkVLC. With DarkVLC, IoT devices in the room can keep chirping small amounts of data 24/7, day and night. It allows VLC to seamlessly transition from day to night. Also, your phone or other smart devices wouldn't need to shine a light to transmit data. To give you a better idea, here's a quick demo of our DarkVLC prototype. We use an off-the-shelf LED as our transmitter, and here is the receiver, a low-cost photodiode. And on the oscilloscope are the signals picked up by the photodiode. And on the monitor in the back, we show the received data in real time. And apparently, the communication is going on, but you can't see the light on. Now you may wonder how it works. Actually, the key idea is fairly simple. We encode data into very short light pulses. As long as the LED duty cycle is low enough, meaning that the light pulses are sparse enough, human eyes won't see them. But light sensors, like photodiodes, can, because they are much more sensitive and can detect the light pulses and decode the data. The idea sounds simple, but making it work is not easy. First of all, it's non-trivial to generate and detect light pulses using off-the-shelf LED and photodiodes. We need careful circuit design to make sure that the LED, to drive the LED at nanoseconds and detect the light pulses at high rate. And second, encoding data into those sparse light pulses is challenging. We can easily end up with extremely low data rates. And third, those short light pulses are fragile and can be vulnerable to ambient light fluctuations. And here is how we deal with it. We stick to off-the-shelf LEDs. We found that it's feasible for most of them to generate 100 nanosecond light pulses. And at the receiver side, we carefully picked up a low-cost photodiode with 15 nanosecond light pulses, with 15 nanosecond rise time, which is fast enough to react with those 100 nanosecond light pulses. And to make sure that our devices fulfill their potential, we carefully design our circuit. And at the transmitter side, we use a MOSFET and dedicated MOSFET gate driver to drive the LED first. And we use an FPGA to generate those 100 nanosecond pulses. And at the receiver side, we design a transimpedance amplifier to amplify those weak light signals. And for higher sampling rate to detect those light pulses, we use a USRP in our current prototype, which offers 1 megasamples per second sampling rate. Now we have those pulses. the next step is to encode data into them. Let's start with some strawman methods. The first one, encode data. Encode data using the presence and absence of the light pulses, like using the presence to represent 1 and absence to represent 0. With our current prototype sighting, we can only achieve 190 bits per second data rates. And another example is to use FSK, which is more robust. And we use the high frequencies in a symbol to represent 1 and low frequencies of symbol to represent 0. And obviously, we will need multiple pulses to represent 1 bit, which would result lower data rates. And our idea is to use the pulse position to encode 10 bits for 1 pulse. And specifically, we further divided the symbol into 1,024 slots, and the slot number in which a light pulse stands can represent 10 bits of data. In this way, with pulse position modulation, we can achieve 10 times higher data rates. And this is the basic form of PPM. And in our future work, we are interested in looking into more advanced PPM variants. And here is how we encode data, but how can we decode them? A conventional method is to find the maximum light intensity in each symbol, such that we can locate the light pulse. But suppose there is some ambient light fluctuation, and the light pulses are added on top of it. If we still find the maximum light intensity in the symbol, we can locate the light pulses incorrectly. And our method is to use an edge detection technique. We first compute the first-order derivative, and then find the peak in each symbol, such that we can filter out the slow ambient light fluctuation and detect the light pulse correctly. And to see how our designs carry out in practice, we evaluate our system in 2 aspects: the system performance and the user perception. And here are some key results. First, we measure our system performance versus different distances. And the x-axis is the distance from the LED to the photodiode, and the y-axis is the throughput, which is the number of bits correctly received per second. And from the result, we can see that our current prototype can achieve 1.77 kilobits per second data rates at a maximum distance of 10 centimeters. Now, you might be concerned about the short distance, but I will come back to it later. And we also did the experiment in 4 different ambient light conditions. There are day and night with and without other fluorescent light interference. And all the results have the same pattern, which shows that our system is robust against ambient light interference. Another benefit of DarkVLC is its energy efficiency. And according to our measurements, the LED power of DarkVLC is orders of magnitude lower than normal VLC. Another key promise of DarkVLC is that human eyes won't see it, so we did a user perception study to look into this. We recruited 5 users, and we showed them DarkVLC and the real light off, and asked them if they think the light is off or not. We did the experiment, we did the user study in 10 rounds, and 5 of them are DarkVLC, and the rest is real light off. But the order is random, and the users don't know the ground truth. There are 2 viewing settings in our user study. The first one is indirect viewing, in which the users look at a piece of paper under the LED and feel the reflected light. And the second one is direct viewing, in which the user look into the LED and feel the light from the LED directly. And here are our results. The percentage represents how likely the user would feel the LED as on. And the second column is the baseline. And interestingly, some users believed that the LED was on, but actually the LED was really off, because they didn't know the ground truth. And from the result, we can we can see that users couldn't see the difference between DarkVLC and the real light off for indirect viewing. But for direct viewing, things are a little bit different. You can see that the users can easily sense the difference between DarkVLC and the real light off in the dark because human eyes are more sensitive in the dark. But this is an extreme case. In reality, we barely stare at the LED during night when we are asleep. And quantitatively, we measure the illuminance generated by DarkVLC, which is only 0.09 lux. And to give you a concrete idea, the illuminance generated by a full moon in a clear night is only 3 lux. The outcomes is promising, but we definitely need a lot of future work. First, the current supporting distance, which is only 10 centimeters, is far too short for communication from the ceiling lights to devices on the table or on the floor. And since the submission of our paper to HotMobile, we have been refining our circuit design to increase the receiver gain and reduce the circuit noise such that we can achieve better signal-to-noise ratio. And now we can achieve 1.5 meters communication distance. Second, the current throughput of our system is 1.7 kilobits per second data rate. It's limited partly due to the single fixed ultra-low LED duty cycle. But actually, human eyes are less sensitive to lights when the ambient brightness is high. So for higher throughput, we can slightly increase the LED duty cycle, but we'll still keep the light imperceptible to human eyes. Also, prior works have shown that we can use the LED itself as a light sensor to measure the ambient brightness. So we don't need to add additional light sensors alongside with the LED. Third, we want to address the coexistence of multiple lights. The light pulses from multiple lights can collide at the receiver, making the decoding challenging. And we plan to look into suitable MAC protocols or even spatial MIMO to resolve the collision. And lastly, we want to implement DarkVLC on mobile devices. There are a couple of challenges. First of all, it is challenging to use the built-in LED to generate those very short light pulses. And our measurement shows that current LED on commercial smartphones can only generate about 30 millisecond light pulses, which is too long for DarkVLC. And on the other hand, the sampling rate of built-in light sensors is also very low, which can only be up to 100 hertz. So we plan to hack into the system and overcome those constraints. And now it's the advertisement time, and we will have a demo, and please come to our demo if you are interested in our project. And that's all I have, and I'm happy to take any questions. Thank you.